Hello, and welcome to this session on investigating real data with me, Mr. McIver, here at the London Central and North West Maths Hub. In order to make sense of this session, you should be fully aware of the content of my previous 4 sessions that look at summary statistics, illustrating data, and sampling strategies. If you're not, have a look at them now. In our session on sampling, we began with the question, are men taller than women? Social researchers often like to start their investigations with a research question, such as this one, but statisticians tend to prefer something called a hypothesis. A hypothesis is simply a statement which we investigate and ascertain whether or not the data supports the hypothesis or does not support the hypothesis. This question, are men taller than women, translates into the hypothesis, men are taller than women. We're going to find out whether this statement is supported by the data. Now, that statement as it stands is a bit vague because we all know that not all men are taller than all women, and so we have to reframe it a bit and say on average men are taller than women. That's a slightly more reasonable question. And because that men are taller than women statement seems to include every man and woman on the planet, we cut down our study and say we're just going to look at men and women in the UK. Now that's as far as we got in the sampling session, but today we're going to cut down the questions still further, and we are simply going to look at men and women who inhabit the town of Specialtown in central England. So our final hypothesis is this: on average, Specialtown men are taller than Specialtown women. So let's have a look at Specialtown. Apart from being almost unbearably twee, what's so special about this particular town? The answer is the population numbers. The town of Specialtown has exactly 3,000 inhabitants, 1,500 men and 1,500 women. And as luck would have it, I have a complete data set for the heights of all the men and women in Specialtown. We are now going to investigate this data set. Notice this is secondary data. And what we're going to do is take a sample of this secondary data and find out whether or not our hypothesis is supported by this data or not. So let's begin our investigation. And the first thing we need to do is get a representative sample of the population. How big should that representative sample be? Well, I've suggested in previous sessions that 5 to 10% is a decent rule of thumb, as long as that number doesn't exceed 1,000 or 2. That would mean between 75 and 150 men and the same number of women. Okay, next question. How will we select our sample? Statisticians always prefer random samples. Humans are very bad at picking random samples. To take a proper random sample, we need to use a bit of technology. The simplest way to do this is to assign a number to every data point in our dataset and then generate some random numbers and pull out those particular data points. Okay, let's do that. Here's my spreadsheet with all my data in. 1,500 male heights, 1,500 female heights, and some weights that I'm going to ask you to work on yourself after this session. First thing I need to do is insert an extra column here and then number all my data points. And the way I do that is I type 1 next to my first data point, put a simple formula in my second row, and then drag all the way down to the bottom of the sheet. To go back home, I simply press Control Home, and now I have numbered all 1,500 of my data points. I'm now going to create a second table on the same sheet which has my sample on it. This column here, I'm choosing column G. I'm going to head random numbers. And the next column, in my case H, I'm going to call values. Under random numbers, I'm going to use a very useful Excel function called randbetween. There it is, randbetween. I click on it. I type in between 1 and 1,500. And then I simply drag down. Now I'm starting on the second row, so I better go all the way down to row number 101. So there I have 100 random numbers between 1 and 1,500. And now I'm going to use the VLOOKUP command. First of all, I type in the function equals VLOOK. Oh, thank you, Excel, for telling me the name of the function. I then say, look at the number on the left, comma. I then say, look at these 2 columns over here on the far left of the spreadsheet. Now, Excel will automatically go to the left-hand column. So, first of all, it will look at the cell on the left. It will find that number down there. I then have to say, give me back the number from the next column along. I put in number 2 because if I call this column 1, it's the first column in the table I've highlighted. I want the number in column 2. Now there's one other tweak I need to add. I want to be able to drag this formula down. If I drag it down as it stands, those numbers are all going to increase by 1 as I go down. So I have to put dollar signs in front of each of my numbers to tell it always to look from rows 1 to 1500. I close the bracket at the end, and now I simply drag down to the end of my list, and there I have 100 random values. I'm now going to use my spreadsheet to calculate my summary statistics. I go down to the bottom here, and the summary statistics I want are all the ones we discussed when we were talking about averages and standard deviation in our first couple of sessions on this unit. First of all, let's find the mean and the standard deviation. Excel simply uses the word average for mean. So if I type equals average, avoiding spelling mistakes, and drag up across all my values, close bracket, that is the mean for my data. So I better type that in. I then want the standard deviation because that is the measure of spread that we use alongside the mean. And the abbreviation for that in any spreadsheet you're likely to be using is equals STDEV. What this will automatically do is in fact calculate the sample standard deviation, which is what we actually want. So there I have the mean and the standard deviation. An awful lot of decimal places there. If I highlight those two cells, that button up here will reduce the number of places after the point. I'm just going to go for 1 decimal place of accuracy for each of those figures. I'd better put in a heading for that one. Now, the other values I'm going to calculate are the median, the quartiles, and I'm also going to tell Excel to find me the maximum and minimum values so that it's easier for me to plot box plots. To get the minimum value, guess what? I type in equals min. To get the lower quartile, I type in equals quart, just choose the first one, quart x. I highlight my data again. I want the lower quartile, so I do comma 1, that's Q1. So there's my lower quartile. I would then like the median, that's simply equals median. The upper quartile equals quart. Oh, there it is again. Highlight the array, and this time choose 3 after my comma. There's my upper quartile. And finally, my maximum value equals max. And I suppose the last thing I need to actually talk about this data set is my interquartile range. IQR is the standard abbreviation, and that is simply equal to the upper quartile minus the lower quartile. So I now have a whole set of summary statistics which I can use to plot diagrams or to comment directly. Now you would have noticed that every time I entered a formula and then hit enter, Excel went and recalculated everything. That's just what Excel does and what any spreadsheet you are likely to be using will do. What this means is that when you work through the questions I set for you, your samples will probably be a bit different from the ones I got when I was doing it, so the numbers in your answer might be slightly different. However, you should find that the overall conclusions are the same. Well, we've calculated our summary statistics. We looked at male heights, we got a median of 178 and an IQR of 9 centimetres. I didn't have time to show you, but we could have done exactly the same thing with the female heights, and in my sample that gave me a median of 164 centimetres and an interquartile range of 8 centimetres. What about my hypothesis, which was, on average, males in this town are taller than females? it looks like the median male height is about 14 centimetres greater than the median female height, while the interquartile range is about the same. If I look at the means, I get a fairly clear distinction between males and females. For males, the standard deviation is 7.1, and for females, the standard deviation comes out a bit lower. Once again, the mean male height of 15 centimetres greater than the median female height does seem to support my hypothesis. Interestingly, the interquartile ranges are about the same. When you look at the standard deviations, the female heights look a bit more bunched up. This is where diagrams can really help to throw more light on what's going on than simply summary statistics. I can use all those figures I calculated in my spreadsheet to draw some suitable diagrams. And the first thing I'm going to do are a couple of box plots. Here are the box plots for my males and females. Well, we've already found just by looking at the numbers that the medians are very different, with the males being about 14 centimetres greater than the females. However, this box plot tells us quite a bit more. For instance, we can see that all the males, in my sample at least, are above the median female height. In fact, practically all the males are above the upper quartile. We can also see that none of the females in my sample even reach the upper quartile of male heights. But if we look at the shapes of the distributions, they are very similar. They both look quite symmetrical, maybe a little skewed to the right, but the interquartile ranges are similar. The male distribution is just shifted about 15 centimetres higher up the scale. So these diagrams strongly support the hypothesis that on average men are taller than women in this town, and also offer considerably more detailed insight into what is really going on. The other diagrams that we talked about at some length in our previous sessions were histograms. So let's draw a couple of histograms for our male and female heights. At first glance, those two histograms look quite different, but if you see, I've actually matched up the scales. The female heights are much more tightly grouped than the male heights. Look, round about this 170 centimetres, we've got more than half the entire group. This histogram is telling me that the female heights are quite a lot more bunched up than the male heights. So we've got our summary statistics, we've drawn our diagrams, now we write up the results. If I was going to hand this in the form of a written report, I would mix up the words I'm going to show you now with the diagrams. But the first thing I do is recall the hypothesis, which was that, on average, the men in this town are taller than the women. I now relate my different parts of evidence to this hypothesis. First of all, let's look at the means. Well, we can see that the mean male height was 15 centimetres greater than the mean female height, and significantly, the standard deviations of the heights for each group were actually quite low compared to the means. That suggests that we can trust these mean figures. If I had a huge standard deviation of 50 or 100, that would tell me there's something funny about this data set. These means aren't telling me very much. The medians and interquartile ranges offered a very similar picture to the means. I haven't quoted all the numbers there because there isn't space. You should put those in too. I then looked at comparative box plots, which revealed remarkably similar distributions for males and females, but with the male heights just shifted 15 centimetres higher. All the males in the sample were taller than the median female, and very few females exceeded the median male height. The histograms offered one new insight, which was that the heights of the female population seemed to be more tightly grouped than the males. And this is, of course, reflected in the lower standard deviation for females. Taken together, all of this strongly supports the hypothesis. So to recap, when you're investigating real data, you start with a clear hypothesis or question. You get a representative sample, you calculate your summary statistics, you draw your suitable diagrams, and then you put them all together in a written report, making detailed reference to the summary statistics and diagrams. You don't just make vague points. Statistics are there to enable precision in your reporting. Now, I'd like you to work through the tasks you've been given.